All right. This is CPSC 323, Machine Learning and Intelligence Systems. Again, I said my name is Graham Morehead, and I originally studied physics and then computer science. And I've been working in machine learning or AI since the late 90s. And I've seen it go through a lot of history, but I'm going to go much farther back than my own history. And in the past, I taught this class last year, but before that, the Palmer would teach this class. So some of the content of the slides comes from him, and some of it's from me. But first of all, I wanted to welcome you guys all to this class. I'm very excited about having you here. And every class will be about half me talking and half me trying to get you guys to talk. So as you think about the next class coming up, think about questions you want to ask, things that you think are interesting. I do see some familiar faces here, and we're going to have office hours. Every class we have, I'll be in my office right beforehand. So for the hour before class, I'll be in my office in Bollier 025. Also, for those of you who are interested, there is a research group that some people have been coming to. Last year, we would meet Tuesday at 6. We will continue to do that this year, Tuesdays at 6. And we're actually going to meet in that back room at the Bulldog. It used to be a faculty lounge, but now it's a little more open. That back room, that's where we'll be starting today. And that's an option for those of you who wish to do some kind of research and you're just looking for guidance or other people to team up. All right. So let's jump in. Okay. Can a submarine swim? I want to get some answers. Be intuitive. What do you think? Yes, I see you nodding yes. You know. Okay. Let's debate. Why yes and why no? Okay, have to be living. What do you think? What if you made a machine that had movements like we're looking for? Would that be swimming? Like a robot fish? It would be closer, but it's so can anyone define swim for me?
I think I disagree actually, because I would define swimming as the act of moving water.
Okay.
And so a submarine follows those parameters. It's working.
All right, let's take a half vote. Raise your hand if a submarine can swim. Raise your hand if it can't. And raise your hand if you abstain. 2 answers. Okay. So there's a very famous computer scientist, Edgar Dijkstra, who said the question of whether a submarine can swim is just as interesting as the question of whether a machine can think. What he was actually saying is, this is not an interesting question. Why would he say that? Why would one of the forefathers of AI say that whether a machine can think is not an interesting question? That's a good answer.
The answer doesn't move us forward.
Yeah, maybe that's it. Maybe it's just a linguistic game. We're just playing around with what's the definition of think, or what's the definition of swim. Let's say you get that definition defined so that a machine could never do it. Submarines still get you there, right? They still do the job they're supposed to do. Computers, whether they can think or not, they do the job we want them to do, right? So maybe it's not an interesting question. But swim was something we kind of could get a definition for. Can anyone define think? Someone try. You're all thinkers.
I think like being able to change the circumstances of the size of the business.
Well, you make decisions based on the environment. That's good.
But also necessary.
So based on memory. So bacteria do this, right? When they're exposed to a virus, they can take in the DNA of the virus, upgrade their own DNA, and the next time they see that virus, that bacteria can act differently.
I guess I would also add that you should be able to make decisions without having previous experience. It's kind of just like using other experiences, like circumstances that don't think bacteria.
Generalize.
Yeah.
Yeah, they probably can't do that. Not that I've seen. Okay, so that's a good definition of the thing. Does anyone disagree or have their own definition? Or disagree with him? No? All right. Well, there's a lot of definitions out there. We're going to talk about some of the underpinnings of all this. Back in the 1600s, yes, a lot of this thought goes way back. In fact, there are things I learned in computer science studying it that were from the ancient Greeks. So a lot of this is just math and reasoning and philosophy. Okay, Thomas Hobbes, in his book Leviathan, wrote, "Reasoning is but reckoning, and argumentation is reducible to calculation." So being a philosopher and making a statement, he was putting that in the realm of mathematics. This guy is pretty important. Okay. Does anyone not recognize Alan Turing? Hopefully you all recognize him. Anyone know why he's responsible, partly, for us winning World War II in the Eastern? Yes. Without his work, we would have not have cracked the Enigma machine. So the Nazis were communicating with each other, thinking it was all encrypted. We were reading all of it. That was a huge deal. And at the time, the best computer scientists in the entire world were at Bletchley Park. That would have been the Silicon Valley. That would have been the beginning of computing, except for at the end of the war, instead of building a thriving computer industry, England disbanded the office and told them all they're not allowed to talk to anyone about it ever. And they had this amazing thing, and they just, let it evaporate. And we had to wait another, I don't know how many years until the actual Silicon Valley started. Anyway, before Turing's work, people thought that maybe for every new kind of hardware, you have to write new software. They thought it was going to be impossible to write a program that can run on anything, but we didn't know for sure. Because of his work, we know that it's possible to make an operating system that will run any kind of software. Now, Alonzo Church and Turing, they came up with some ideas that help us understand computation. Computation is an operation that begins with some initial conditions, gives an output, which follows from a definite set of rules. Everything is defined. Now, later on, they came up with this idea of a non-deterministic computation device, which can go down multiple pathways, maybe in parallel, maybe one after the other, but non-deterministic and deterministic are two ways of looking at the same abstract thing. These abstract machines, we call them. Think about it as a set of states or a set of things. You can change the state of this, and this might be a memory module. Maybe it just holds a 1 or a 0, or maybe it holds a character that you just read. And this machine, just like you were talking about, a thinking thing will have some memory of the past and maybe be able to generalize. But it has to have that memory. That memory is something stored within the state. They also said that any real-world computation can be translated into an equivalent computation involving a Turing machine. A Turing machine is one of these types of machines. Have you all learned about that already? All right. We will cover it a little bit anyway. Okay, first of all, the Turing test. Has anyone heard of a program that passed the Turing test? Can someone explain what this is? What's going on here?
It's like, so you have somebody that tries to predict, it's like they're having a conversation with a machine or a real person. And that's like the fast things on the brain.
And they do this with multiple people. So they'll have the same person be in the same computer program A, but there will be multiple people that take the place of C and give a whole bunch of questions. And if you can fool more than half the people after a certain number of questions, I think it's 20, then maybe it was 30, but if you can fool more than half the people, then A has passed the Turing test. Now, recently, maybe a year ago or so in the news, there was this computer program that was able to pass the Turing test with a whole bunch, maybe more than like 20 participants. And the way it did it was by pretending to be a Bulgarian exchange student. So, of course, it didn't quite understand you quite right. You got some answers wrong, but you were very forgiving because you knew it was an exchange student when it really wasn't. That's one of the techniques that people can use to try to trick you. Is there a situation in life where you have come across a computer program trying to be a person?
I feel like every time you try and message someone for help on the website, you get a bot.
Exactly, that's one of them. You also raise your hand?
Spam emails.
Yes. How about spam texts? I get spam texts, a new one, almost every day. And it almost always starts with them trying to guess my name. And some funny ones recently, I got one, hey, Etta, do you have any extra baggage? I'm about to get on the plane. My name isn't Etta, but they try a different name every time. I always go along and pretend that I am that person. And then at one point, it'll get me routed to an actual human. But a lot of these, I believe, are initiated by bots. And it's, typically for a scam. But chatbots have been around for a long time. And a chatbot is essentially what the Turing test is testing. Now, I imagine that a lot of programs out there have, in effect, passed the Turing test in real life. They've tricked people out of their money, or gotten them to sign up for this or that, or been used for phishing. But there's something that someone has thought of which is harder than the Turing test. What would be harder to pass than Turing? And it would apply to the same situation. You have an AI, you want to see if it's truly intelligent. There's a movie about it.
There's some sentences you can feed to like a computer, it just will be solve it. You can give it a sentence and a question based on it. Answer correctly.
That's a good point. Okay, this makes me think of GPT-3. Who here knows what GPT-3 is? You do? What is it?
It's like AI. I think it's related to GitHub, but it's supposed to help you with like suggestions for writing software.
It can be used for that. It can be used for a lot of things. It is a transformer. And we will be getting into this much later in the course. But another way to say it, it's a very large language is the multi-headed attention network. Anyway, there's a lot of ways to say it, and you've probably heard about that program at Google. They call it Google Lambda, and there's this employee who said, it's conscious, we've got to give it rights. And Google fired them. Remember that? So first of all, does anyone here think it was conscious? I would say you can raise your hands. Who thinks it's conscious? Who thinks it's not? Conscious first. Who thinks it was conscious or sentient? Okay, who thinks it was not conscious or sentient? Okay, we're in pretty broad agreement. One abstainer? Did you abstain? You raise your hand? Okay. So the reason I believe it was not sentient is because it's just matrix math. If you hired a whole lot of people to do this with pencils on graph paper, you would get the very same outputs that he got. It's just matrices being multiplied by each other, and eventually you get this long vector, and depending on which field has the largest value, you choose a certain word next, and then another word, and another word. If you had humans, pencils on graph paper would get the same answer. Graph paper is not conscious, last I checked. Not in the way that we think of ourselves as conscious. Now, that same type of model, OpenAI, one of Elon Musk's companies, they made one too. And it was in the news a lot before Google Lambda was in the news, but same technology. And someone asked it a question you might never think of asking. And this is what really trips them up. Someone asked GPT-3 if a flock has 5 dogs and 100 sheep, how old is the shepherd? As a human, if someone asked you this question, what would you say? Throw me some answers. What? Yeah, that's a good answer. What's another one? What's a more informative response that a human should give? Is this a riddle? That's a good one. Yeah. So answer a question with a question. That's something a human would do. Human might also say, this doesn't make any sense, or those things are totally unrelated. Why are you asking me this? You're annoying. Well, GPT-3 doesn't know get annoyed. It doesn't know when things don't truly make sense because it doesn't actually reason at all. All it can do is tie together words that go together. And to get there, to learn to do what it has done, it literally read the entire internet. GPT-3 was trained on 1.1 million years worth of English. It's not how a human learns. It learns just by brute force. Have any of you had a parrot that could talk or interacted with one that a friend had? You remember it saying anything that sounded like it was thinking?
No, it was just kind of repeating the same phrases.
Yeah. Well, there are some videos online of this woman who trained a gray parrot for many years. Gray parrots, I think they live longer than humans, but she trained for a long time. And there were certain times where she said something and it said something back that I think it understood. I don't believe it actually did. And GPT-3 is kind of like a giant parrot that can live for a million years. So when they asked it this question, it said very confidently, the shepherd's 125 years old, because that is the only age at which you could have an equal number of sheep and dogs. Where on earth did that reasoning come from? What are some guesses where that reasoning came from? Remember this thing learned by reading the whole internet.
SAT questions.
That's a good idea, yeah. Any more guesses? Yeah, just English literature, just like these sentences sound fluent. They kind of go together. They kind of have to do with the question, so why not, right? But of course, there is no real thought behind it. And I'll mention this again later in the course, but it is the computational equivalent of something called Wernicke's aphasia. It's a neurological condition. And colloquially, it can be called word salad. If someone has Wernicke's aphasia and you listen to them having a conversation, it's very fluid. They're talking, you're talking, they pause when you're talking, they go back and forth. But if you actually look at the content of these sentences, you realize there is no train of thought being communicated. It's very interesting condition. And this AI, GPT-3 or Google Lambda, it has a really advanced version of Wernicke's aphasia, where it can tie together sentences that make sense to go together. But if you look at the whole thing, there really is no thought behind it. So it's not thinking like you or I, but in a limited context, it can pass the Turing test. Now let's talk about what's harder than the Turing test. Who has seen this movie? It's a very well done movie. Now, what is the beyond the Turing test thing that he brings up? You remember? Well, the Turing test is hard enough. You don't know if it's an AI or a real intelligence thinking thing or not. But what if you do know that it's not a human? So he says true intelligence is when you know for a fact it's not a human. It's a machine. Can that machine still convince you that it's thinking, that it has a mind, that it is sentient? That Google Lambda example, it convinced someone it was sentient. It convinced them well enough that he got fired, spoke up about it. Of course, if I was in the Google marketing department and I was like figuring out ways to get extra press for Google, I'd be like, you know, we make people convinced that we have something really cool. Let's pay one of our guys to pretend to be a whistleblower, that we have a sentient program, and we'll fire him and make it a big deal. That'll make people think we have something awesome, and we're trying to cover it up. Anyway, I highly recommend that movie. Okay, this is what a Turing machine would look like if you made one. Someone actually did make one. But it's more of theoretical concept. So imagine an infinite length tape. Just goes on forever in both directions. And you have this thing here that has an internal state, and it knows rules that it can follow. And it can write a symbol to the tape, or it can erase, write a new symbol, and it can move. Sometimes it just reads and it doesn't write. And this thing, eventually, you will end up with something on the tape. Whatever's on the tape at the beginning, you consider your input. Whatever's on the tape at the end, you consider your output. And if you're talking, binary numbers, ones and zeros, and you want to multiply them, I think you just put them together. There's a lot of things that are simple to do on a Turing machine, other things that are way more complex. But one of the things Alan Turing proved is that everything we can compute on any computer can be computed on the Turing machine. That means you can do World of Warcraft multiplayer on a Turing machine. It would take literally forever to update for one step, for 1 second, but it could be done. Everything can be done on a Turing machine. Now, why on earth would it be so important to create this theoretical construct and use this in the literature? Why would this be important? Why did this change everything? Have you guys, any of you taken theory of computation or automata? No? So each one of these theoretical machines, Turing machine is just one, and a whole class of them, is a way to think about computers in a more simplified way. And if you have this more simplified way, you can do proofs. This is where we did proofs, like, ever heard of the halting problem? Who's heard of the halting problem? Can you explain it?
I've heard of it, but I don't remember.
So the idea is that it would be nice to know for a computer and a given input whether or not it's going to finish its computation quickly or go on forever. That'd be nice, right? Have you ever had a spinning wheel on your computer and it's annoying, and eventually you have to, turn off that program or even reboot the computer, right? How do you think we're going to solve that? How are we going to write a program that can always determine if something's going to stop spinning or it's going to go on forever? Answer is, we'll never be able to. It's the problem we'll never be able to solve. And the reason we know that is because Alan Turing proved it with the Turing machine as the construct. I got to meet this guy, and this is something he told me personally. He said, we humans are nothing more than non-deterministic Turing machines. And we're not even that, because we don't have a hidden end. So that little Turing machine thing that we've been using in computer science to prove things, apparently he thinks that's more powerful than your brain. I don't know if I believe that. What do you guys think? Are you more than just Turings? Or are you less than Turings?
I feel like if you said it would take a Turing machine and running and just update 1 second.
Yeah.
Maybe they could do more given.
Maybe that's it. We're better in the moment, you're saying. How about comparing us to computers in general? If you take Turing machines, this means all computers. What's the difference between a computer and a human? Is Yoshibak right or wrong?
Just close around the situation. Most likely have some sense of it, or you're like the hardware focus. We just have something that can make sense of.
Now, what Yoshibak thinks is that we just have the wrong program. Once we get the right program written, it will act like a human and maybe the right hardware. What do you guys think?
It's really hard to.
Have you ever been in situations where emotion was not part of the picture at all? Yeah. Do you think emotions are needed for what we have as far as the way we understand
Society.
Good point.
Would you say like computers can like imitate emotion? So like if you feed in enough data of how a person reacts to certain events, at one point we could make those things kind of like imitate the sort of well.
Seems like we don't. Yeah. That's right. I'm never stuck, spinning in my head and I'm not responding. Yeah. Have any of you ever interacted with a real sociopath? I think I have. They're imitating emotions. They're not actually feeling them. But the real dangerous ones are people who are high on empathy, and because they can sense what you're feeling, but they don't care. Those are the truly dangerous people. And one of the game theory things that happens in human societies over time is you have people who emerge who are able to trick others into thinking that they really do feel those things. But then everybody else is trying to sense at the same time, can I really trust this person? Do they really feel that? So imitating those emotions versus having the emotions, it's a difference we all care about. And right now, if we were to program emotions into a computer, it's really just a register in a field, right? It's the volume variable. That's not a real emotion, right? I mean, Lex Friedman asked Joseph Bach about this kind of thing, and he asked him about suffering. And Bach didn't have a great answer. It was something along the lines of, it's just a matter of, the computation or something like that. But I think Friedman had the right question. It's about suffering. If an AI could suffer, that would change how we deal with it, right? What would we have to do?
You have to think like all the ethical issues of program off.
Yeah. And what if there's no way to make it run without it suffering? Then you have to turn it off, maybe. But maybe you have to ask it first. Are we more than Turing machines? Okay, Herbert A. Simon on the right and Alan Newell on the left said a physical symbol system is the necessary and sufficient means for general intelligent action. A physical symbol system is merely, you have a symbol for this, you have a symbol for that, and you have some logical rules that can connect. You say, if A then B, then every time you see A, B must be true as well. And you can build a world of logic based on that. And there are some, there's first order logic, there's different kinds of logic out there. And in grad school, typically they ask you to write a computer improvement. And I've done this. And you can write something that takes in a bunch of rules written in symbols that the computer assumes to be true. And then you can do logical reasoning on those rules. Now, this is okay. There's a lot we've done, though, in deep learning that is beyond what he's describing here. Deep learning is typically not about symbols. It's about taking in something like a vector, something that is more like a floating point value or a set of floating point values. You take those as inputs, and then you give something an output, which is usually a floating point value or a set of them. And you can reduce that to a symbol afterwards. Like the way GPT-3 works, the output is a set of floating points. And the one that's the highest is the one that you say, we're going to use the symbol that this field is connected with. And then it becomes a symbol. So these guys, they were leaders in that time. This is a long time ago, before deep learning. Deep learning is not the whole picture either, though. Okay, now in the 1940s, we had ENIAC, which is this massive computer the size of a room, and it was used mostly for creating the numbers that would go into firing solution books for the military, like where you should aim the howitzer to go a certain distance, things like that. But this room-sized computer setup reminds me of a new kind of computing that's emerging right now that takes up this much space. Does anyone know what I'm referring to?
Cloud.
No, quantum computing. Cloud computing, yes, you're right. It does take up bigger rooms than that, but that's to serve millions of people, you know. But quantum computing, just one quantum computer can take up a lot of space. Okay, AI really started as a term in 1956. These guys all got together and had a conference in Dartmouth, New Hampshire, and they began it as a field trip. Before that, no one really was discussing it or researching it. Claude Shannon invented information theory, which is one of the most important things out there. And we will discuss that some this year. Alan Newell, we just talked about him. John McCarthy is very famous. Marvin Minsky at MIT, he came up with this idea called society of mind, saying that in your brain, it's not one processor. It's really, you know, billions of them. They're all competing with each other. And whichever ones win at any given time is what you end up thinking about. Of course, everyone here is pretty important. Okay. Is there a clock in here? No. Okay. So AI has gone up and down over the years. And this is all before, you know, before I remember anything. But in 1970, Marvin Minsky told Life magazine, in 3 to 8 years, we will have a machine with general intelligence equal to a human being. It was so off. These guys were so optimistic about what we could do. And I believe underestimating what humans can do. Like, even just think about our visual system. When you are outside on a bright day and you look down and you see a piece of coal, it looks black, right? It looks dark black. But then you go inside into a dark room and look at a piece of paper. It looks white to you, right? But there's actually more photons that were bouncing off that black piece of coal into your eye than would be bouncing off of a white piece of paper in a dark room. Why does the paper still look white to you and the coal still look black? Context, yes. How is your brain interpreting that context? What is it doing? Well, here's another question. Have any of you guys seen the dress that everybody disagreed on color? All right. So here's another thing we can all disagree on. Who saw the dress and could see blue and black? Who saw white and gold? Yeah, I saw white and gold. And even once I saw a picture of the actual dress in normal lights, I couldn't see the right colors. It still looks white and gold. And I can't imagine how you guys see it correctly. One of you guys who sees it correctly is blue and black. What was your brain doing that helped you do that? Color shade. It's like one part is lighter than the other. Ah, okay. And your brain just does it instinctually, right? What other things do you think your brain does for you instinctually? Besides color process? Breathing. Breathing, yes. And you breathe differently in different situations, right? Based on context. If a rabid dog got in here, you start breathing a lot faster because your body knows you need more oxygen. How about sound processing? The words I'm saying right now. What is your brain doing to that sound? Any thoughts?
I guess if we like relating it to past memories of hearing the same sounds.
Okay, I'm going to say two letters that in another language are totally different. Shh, 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 shh. Those are totally different letters in Russian and Ukrainian. They're very different letters, and they're different words. But to the American ear, they don't sound different because we learned to ignore that difference. Whereas in other languages, there are things that they learn to differentiate. Do any of you speak other languages, and are there things you know that are different in another language, but to English speakers it sounds the same?
I don't speak it, but like Mandarin has like tonations, so like they'll say the same word essentially, but
Yes, there's this famous poem in Mandarin of the stone and the lion and the poets or something, and every word sounds to an American ear like shh, like shh, 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 shh. I can't imitate it, but you can look it up online, and it's kind of a linguistic amazing thing. But brains take in context, and we expect something in the next instant, and we change what we hear to either fit that or not fit that. So I spent many years working in speech recognition. And it wasn't until we started to duplicate what the human brain was doing with speech before we realized just how hard it is. This is part of why Marvin Minsky was so optimistic. He didn't know how hard our brains are already working and how much they're already doing. For instance, we would take sounds that maybe would correspond to certain phonemes. A phoneme is just part of a sound that we make in speech. So let's pretend we had the phoneme for the letter S, the S sound, and it was approximately here. Let's say we plotted it all on a two-dimensional area. We would do this. We would actually print these out and look at them. Now, they were actually in a 45-dimensional space, but it's difficult for humans to understand that, so we brought it down to 2 dimensions. So you have an S, and then you have a T sound for the letter T, and then R for an R-type sound. And let's say we're just looking at consonants and not plotting the vowels. And then we have someone, a bunch of people say the word store. You would think that it would start here, go to here, and then there. But then we'd actually record people saying the word store, and to the human ear, it sounds perfect. It sounds exactly like the word store. And one person, it'll be like this. Another person will be like this. Another person will be like this. They're not going anywhere near the actual sounds and at least not as the computer would understand it. Somehow, the brain is cleaning that up. Somehow, when you see that piece of coal outside on a sunny day, or the piece of white paper inside on a dark day, your brain is cleaning that up. Now, we all have this amazing capacity that we inherited to do this, but we don't all have the same capacity. As we just saw, we didn't all see blue and black for that dress. Some of us saw white and gold, but the dress is not white and gold. So somehow, some of us are lacking in one of those key processes that the brain is using. Now, how do we know that the visual system for the human is not perfect?
Those optical illusions.
Yes, optical illusions trick us even when we know they're there, right? Have you guys heard of optical illusions for AI? They're called adversarial examples. We'll discuss it later in the course. But you can take an AI that's really, really good at recognizing animals and show it a picture of, let's say, an orangutan. And says, this is an orangutan, 100%. But then you go in and you change this pixel here a little bit, and this pixel over here just a little bit. You make such small changes that as a human, you can't even tell it's different. But then the computer says, it's a panda, 100%. You can trick the AI. So there are optical illusions for AI, and there's optical illusions for computers, and right now they're very, very different. But the brain is doing a lot of heavy lifting, and we didn't know just how much until we had to do it ourselves. We didn't know how much it was doing with vision until we had to do artificial vision. We didn't know how much it was doing with speech until we had to reverse engineer speech ourselves. Anyway, in the AI winter, remember AI started in 56, people were really optimistic for a while, but 74 to 80, people lost, a lot of their hope. But then we had some good times, right? Expert systems came along. And what expert systems were intelligence programmed into a bunch of rules. Like, let's say we sit down with a whole bunch of experts and ask them questions. What do you do in this situation? What do you do in this situation? What do you do in this situation? And the answer would be whatever they do. And then if you get enough of them, then you can, get the minds of all these experts, and you can take someone who's not an expert, and they could do what the people would do in that situation. Or computer could do it. What are some fields in which this would be really helpful? What? Math? Yep, math is one. It's good. What else? What professional, if expert systems work perfectly and were wonderful, what professions would be in danger of being replaced by an AI? Yeah. Imagine if you go to see your doctor in the future, and instead of the doctor, it's a chatbot, and it asks you some questions and maybe run some tests. Would you trust that? Yeah, why?
I'd say it kind of reminded me of like those coin machines, like they wouldn't tell you how much the changes were too quickly, so they put a delay in it because they would believe that it was like accurate. So I feel like it's kind of the same kind of thing where it has like the reason behind it. It's correct a certain percent of the time that's better than doctors.
Yeah. What could go wrong?
Doctors might notice like subtleties in how you explain the situation that a computer would, and that might affect how you diagnose it.
How about, oh yeah, correct.
Also, maybe like you said, changing one pixel could send the bot off in like the total wrong direction, whereas a doctor might get it slightly opposite.
Yeah. Don't you feel like humans have a self-correction mechanism somehow? That we know when we're doing something that makes no sense at all, and computers don't. The other thing that's interesting about expert systems is, of course, it's gathering knowledge from many, many people, and you think the more, the better. But what happens if you have a massive voting system like that? Do you think there's something? Is it better to have one really good expert, or the aggregate knowledge of a whole bunch of maybe medium experts, which is better? Why?
Decisive. And just that way you have like less to compare, I guess.
Does it depend on the type of question you ask? If it is, does, how? Have you guys ever heard of the wisdom of crowds? There was this famous book called The Wisdom of Crowds, and it looked at these old examples, like there were a couple of different things that would show up at fairs a lot of times. One of them was they would have a big ox as you walked into the fair, you know, however an ox looks. Not a very good ox. But there's this big ox and tail, 4 legs. And you have to guess how much it weighs. And if you guess right, you get a prize, like $100 or something. Another one is they would have a giant jar of jelly beans. And you have to guess how many jelly beans are inside. These two problems are very well suited to aggregate knowledge, to having a whole lot of people guess. And there were times when they had an expert on ox weighing, and they have a number of these experts, and each one of the experts would try to guess the weight of the ox. And then they would compare that to the average of a whole bunch of non-experts. Who won? Yes. The average of non-experts is consistently more accurate than any single expert could be. Does that surprise anybody here? Same thing with this. Now, what surprised me is that there are situations where that totally breaks down. And one of them is very close to my heart. So I'm from Boston. Do any of you remember the Boston bombing? Patriots Day, the morning of the Boston Marathon. A friend of mine actually was almost killed. He actually moved 5 minutes. He was walking through the crowd, and he was right next to where the explosion was 5 minutes before. Almost killed. Afterwards, everybody in the community wanted to help find these guys. And thousands of people online were combing through footage. They released footage, pictures, security camera footage. People were following leads. Thousands of people. None of them turned up any leads of any use at all. They were all dead ends. Them voting together and working together was just nothing but dead ends and a waste of time. But a few expert detectives very quickly figured out the right clues and followed the right clues and were able to find the guys. Why was this so different than guessing the weight of an ox?
This is more than just interesting.
How many variables are there, or how many degrees of freedom? There's millions of things, right? So with an ox, it's just one number. How much is away? Jelly beans. How many jelly beans are there? One variable. Or maybe you're looking at the volume, so it's 3, but it's so much simpler, right? So what could go wrong if you had an expert system as your doctor instead of an actual doctor? Yeah, or do a good job. You might kind of average them out and not get to anywhere meaningful.
If it works, like you described it, you provide the symptoms that you're having. There might be symptoms that a doctor would investigate to put in the sort about yourself
And it also seems like if this technology actually works right, WebMD would be doing it right now, and you wouldn't need to go to the doctor. But we still have doctors. So during this time, we thought it was good times. Expert systems were coming online. People had a lot of hope in them. Japan had their 5th generation project, which I don't really know what that was because I wasn't around. Connectionism is neural networks. Neural networks originally invented like 1958. That's the whole idea of you get those floating points and you're converting them to other floating points through a number of transformations, not symbols. The expert system would work with symbols. Connectionism is just connecting things that are like brain cells, but simulated. No. Anyway, at the end of these good times, basically the industry was starting to lose patience. Of course, government funding dried up. Because people are like, yeah, you promised us all this stuff, and you keep saying the same stories, but it never comes. You never get true intelligence. Expert systems did not work as well as hyped. And they could not learn new stuff. If these changed, they did not respond. There's a collapse in specialized market for AI hardware. So Lisp is I would think a very annoying language. I had to learn it. And that theorem prover I told you about, I had to write that in Lisp. You might have to learn Lisp at some point. I find it just totally annoying, but some people love the way it's organized. Maybe it suits their brains. Lisp operates on 2 memory units, a car and a cutter, they call them. And there's hardware that was basically an implementation of Lisp in hardware. And people wrote Lisp programs that ran very efficiently on this hardware. But imagine that. Imagine having a computer that it's not going to run Python, it's not going to run C, C++, C#, Java, JavaScript, none of that. It only runs one language. That's very limiting. So I think it makes sense that that company, or the companies that made that stuff, totally collapsed. But I had a professor in college who was still grieving that all these years later. So this is the AI winter number 2. Now, I graduated college in undergrad in 1995, and just at the end of this, but still it was in the air. And one of my good friends sat me down at the college. I told him, I took this AI course. I loved it. I'm gonna not do physics, even though I got my physics degree. I don't want to do physics anymore. I want to do AI. And he was like, Graham, AI is dead. It's not going anywhere. AI is an industry. You're not going to get a job. There's not any companies doing. There's no money going into it. He was a really smart, well-educated guy. Had his master's degree in business and was working in the field and stuff. He was so wrong, though, right? He was so wrong. So much, not just wealth, but companies and careers and everything has been spawned way after this. So just because there seems to be a dip at different times, that doesn't mean the field is going away. We had good times again. Machine learning started gaining ground. Coined by Arthur Samuel in 1959, way before my time. Machine learning has been somewhat separate from AI in some people's minds. I don't think you should think about it as separate, but some people have. They think, okay, machine learning is using statistics to learn how to solve problems. AI is using symbolics, some people say. Remember your symbols and logic versus floating points going through a neural net. But just think of them all as different parts of AI. That's how I think of it. Now, in the late 90s and early 2000s, we had much more powerful computers and better data, more data, less expensive. These 2 things together enabled us to do what they had been imagining since the 50s. We couldn't afford it. have huge neural networks absorbing tons of information. Okay, so after, decade and a half of good times, what do you think comes next? No. First of all, this guy, I'm Ben Goertzel. He's one of the guys who started modern machine learning as an easy thing to do. He came up with Weka, him and a few other people. Ben Goertzel also now he does artificial general intelligence, at least he believes it will be. Sophia is not artificially generally intelligent yet, but this is just the model that he's working with, the Hanson Robotics. And he really does wear that hat almost all the time. And I got to meet him. He's a very unique guy. One of the things he's most excited about is getting up on stage and jamming with his band, and Sophia is right up there with them. And she will, do spoken word. Not quite singing yet, they're trying to get to singing, but spoken word. And the words she says are words that an AI came up with. So it wasn't even human written. So he started a lot of these tools. Weka was the first tool that I used in machine learning. You will, in this course, use scikit-learn and either PyTorch or TensorFlow or JAX. And these tools make it so much easier. But Weka was the first of these tools. Anyway, after that good times, we actually had great times. In 2012, there was the ImageNet moment. Who knows what that was? So ImageNet is this large data set of images that have been captioned. That humans have come along and said, this is a picture of a cloud, this is a picture of a boat at sea, or whatever. And then the idea is, can you write a caption seeing the image? Just having the computer come up with it. And that means the computer has to understand the image, right? Well, people have been trying to do this for years, and they've been reaching certain levels of success. 2012 was the first year that deep learning beat everybody by a long distance, and then never looked back. Nobody could ever beat deep learning ever again after this moment. So after 2012, that's when things really started to kick off. What do you guys remember from the world before 2012? Name a couple memories from before that time.
Recess, but great.
All right. So did any of you guys use speech to text before that? Like talk into a tablet or a phone and see your words come out? It was annoyingly bad before this. A lot of things were annoyingly bad and have gotten a lot easier and a lot better since 2012. We all thought that we would have another AI winter. We didn't. And we may never have one again, unless there's some kind of world war, which I hope not. But what's coming next could be even better. Unfathomably good times because of quantum machine learning and perhaps artificial consciousness, if we can even define it. Now, this is a graph, which is approximate, but it's numbers of photos taken each year, only until 2011. The red is all photos. The pink is analog photos. Those old cameras with film. Who here has actually used one of those? All right. I used them for years, of course. And I even learned how to do black and white in the laboratory and develop it and print it and all this stuff. Gosh, it takes forever. And I remember as a kid thinking I had a camera and thinking ahead of time that every picture I took, okay, once I use up this roll, it's another, $10 to get it developed. And then another $8 or buy another roll of film after that. It was expensive. And as a kid, you don't have much money. So, of course, people didn't take many photos back in the day. But they started to take more and more anyway. When do you think the digital camera was invented? Somebody guess a decade. No. After? Before? After? Mid-70s. It was invented in the mid-70s. What's the most famous camera company from that time? Have you ever heard of Kodak? Kodak was not just the biggest camera company at the time, they were one of the most profitable companies in the entire world. I think they even competed with like oil companies. They were super powerful, super rich, and it was all on analog photography. They invented the digital camera in the 70s. And it was just a research project. They invented the CCD, the charged coupled device that would receive photons and turn it into an electric impulse that could then be recorded and used in a file. They invented that in the 70s. Around mid 2000s, it really started to take off. Early 2000s. I had my first digital camera maybe late 90s, something like that. They sucked for a long time. If you're an executive at Kodak and you see this digital camera and you see, okay, it's expensive and it sucks, you think, this is not going to be a big deal. When do you think they realized it was a big deal? What year? If you were looking at this graph, which year would you say digital photography is really important? Yeah, just a little bit after 2000, maybe halfway between 2000 and 2011. By 2011, digital is everything, right? And this is a long time ago. Now, there are more photos taken just on iPhones in, I think, 1 month than have been taken on paper or analog cameras in the history of all photography. So many pictures are taken. But these executives could not see. Is Kodak a big company now? No. Why on earth? They invented the digital camera. Why are they not even richer now? Some guesses. You guys think about this. Just take some wild guesses.
They sold the rights.
That's a good guess. That's not what happened. They did see everyone else catch up with them and go far beyond them.
They didn't see us in the research. They probably thought, hey, companies looking to this or different demographic.
There were age differences. Young people think differently than the executives at a big company. If you make a digital camera, how much more money do you make with each digital picture that your customers take? Zero. Were executives excited about making zero with each new picture? They just stuck to the old model. And there's this old saying, it's really hard to understand the truth when your paycheck depends on you not understanding. They had the technology, they invented it, they could have been the leaders and they weren't. And this story gets repeated again and again in all forms of technology. The reason I show you this is because it's an exponential curve. Computing has and always will be, I believe, on an exponential curve. It's really hard to imagine where this curve goes, though. And these guys could not imagine it. They think about this. As it started to get better and better, digital photography was almost as good as analog. There came that day when they were just as good. And the tendency is to think, oh, now they're each other for a while. No, like the very next year, it's doubly as good. And the very next year, it's 4 times as good. And there's just no keeping up. That's how technology flips occur. When quantum computing comes online, quantum machine learning, it will be like this. It will be to normal computing what digital photography was analog. This time is coming. And you guys are going to have to work in that field. And the one thing about this field is that it's always changing, and it's always changing faster and faster and faster. And that's just part of life.
When did you get this?
Quantum computing, there, as of 3 years ago, there were 4 brands of quantum computing that you could rent on Amazon. IonQ, D-Wave, Rigetti, and one other. And a 5th one, IBM, you could log on to their quantum computer ever since like 2014, I think, something like 2015. These are actual quantum computers that work. Now, they're noisy. They're as noisy as our normal computers were in the early 70s. So if you think about going from the 70s to now, that's about how long it's going to take to go from quantum computing as it is now to really, really useful. Maybe another 40 years. It's going to be really, really useful. But it could be way faster than that. We're getting better and better at making these curves. All right, so class is almost over. Any last thoughts, any last questions? Read the syllabus. It describes the course in general and how homework is going to be done. Your first homework assignment will start Thursday. I'll explain it then. It'll be due a week later. Thank you, everybody.